We have previously looked at using marginal costing techniques to create an optimum production plan where there is one scarce resource, limiting factor analysis. Here we will increase the complexity and look at using linear programming to produce a production plan if there are two or more limiting factors. Linear programming techniques solve problems of a profit maximization or profit or cost minimization given situations where resources are limited, i.e. when it would be naive just to consider production based on the maximization of contribution without considering resource utilization. So linear programming is concerned with the management of scarce resources where two or more activities are competing for those resources. There are two approaches we're going to take. Firstly, the graphical approach, and then secondly, using simultaneous equations. The graphical approach has got 5 steps. Take them step by step. We start with defining the objective, usually the idea of profit maximization, and then look at the constraints that are stopping us from achieving that objective, plot the constraints on a graph. We then identify the feasible region. That'll be easier to see when we look at it on a graph, and using that feasible region we can solve the optimum production plan. Let's just look at this example. Here we have two products. The first thing we're going to do is we're going to take these products, A, and have them represented by an algebraic symbol. And so A is going to be represented by x1, and B is going to be represented by x2. We do this, in this case it looks a bit daft. I could have just used A and B in my equations, but normally you're given product names, like you might be given the first product is a wardrobe, the second product is a table. And instead of having those words in the equations, we use the symbols, usually x and y, sometimes A and B. So once we've got our symbols to represent our units, x1, product A, x2, product B, we then look at our objective function. What do we want to achieve? Well, we want to maximize our contribution, and we can do that because we know that contribution per unit earned from each product is £4 for x1 plus £3 for x2. That's our objective function. Once we've got the objective function, we then look at the constraints. Here we've got our constraints. Machine 1, machine 2, machine 3 is restricted to 8 hours, 5 hours and 12 hours respectively. So let's look at those constraints. So with machine 1, each unit of A requires 1 hour of machine 1. So with 1 hour of machine 1 for product A, and then for product B it has 2 hours of machine 1. And then with the restrictions, we're restricted to 8 hours, less than or equal to 8 hours. We can do exactly the same with machine 2. With machine 2, for 1 hour for product A, plus 1 hour for product B, and that's going to be less than or equal to 12 hours. And for machine 3, we've got 2 hours for product, 3 hours for product A, and then we'll have 1 hour for product B, and that's going to be less than and equal to 12. Sorry, my mistake, that should be 5. Read the question, Sean. Okay, So there we've got our three constraints, machine 1, machine 2, machine 3. We're now going to think about the step-by-step approach. We've defined our variables, we've stated our objective function, and then we've constructed our constraints. Now we need to put them on a graph. Plotting the constraints is not difficult. Oh, before I say that, don't forget the non-negativity constraints. We always have to state that our two products, x1 and x2, have to be greater than or equal to 0. They're not negative. We're now going to plot the constraints for machine 1, machine 2 and machine 3. If we look at machine 1 to begin with, we've got the equation for machine 1, x1 plus 2 x2, and this time we say equals to 8. And what we can do, we say if x1 equals 0, x2 is going to equal 4. And then if x2 equals 0, x1 will equal 8. We then take these points and we plot them on the graph, where x1 is 0 here, x2 is going to be 4. Where x2 is 0, x1 is going to equal 8. Once we've plotted those two, you take a ruler and you join those two coordinates. We can do exactly the same with machine 2. x1 plus x2 equals 5. If x1 is 0, x2 is going to equal to 5. If x2 is 0, x1 will equal 5. And we can plot these on the graph. It's the pink line here, those two coordinates, and join that up. Do exactly the same with machine 3 with the plotting the constraints, and that's the green line. Once we've plotted the three constraints, we can identify the feasible region here. All of this below this area is the feasible region, and our solution is going to be one of the points on that feasible region, either there or the intersection of the purple and blue line, or the intersection of the purple and green line, or this point here where the green line meets the x-axis. To actually decide which point is going to be the optimum solution, we then have to plot the objective function. The objective function, we take our formula and then we assign an arbitrary figure. Now this is often difficult for students to understand. Why did I pick 12? Well, I wanted a figure that is going to fit in with my scale. So I wanted to have a figure that is going to give me answers, or a line I can plot using figures. The highest figure I've got up there is 12 for my x2. I don't want figures above 12. It could be below. So I don't want figures that are going to be outside my range. The reason I picked 12 was to multiply those two together, and that equals 12. So now to plot my objective function, if x equals 0, then x2 is going to equal 4. If x2 equals 0, x1 will equal 3. And so I plot the objective function, which in the graph is the red dotted line. x1 is 0, x2 is 4, x2 is 0, x1 is 3. To work out what the solution is going to be, I'm going to take a ruler and slowly move this forward. And then once it reaches the last point in the feasible region, that will be my solution. And if I do that, it's that point there. The intersection of constraint 2 and constraint 3. And there I can read off what the answer is going to be. It will be 3.5 and 1.5 to read off on my graph. Constraint 1 is not a binding constraint. Constraint 1 gives me some slack. We'll talk about slack later. Constraint 2 and constraint 3 are binding. So if we look at our optimum point, the optimum point is the intersection of those two constraints. So we've got our solution, we can compute our contribution, and we notice that constraint 1 is non-binding and not relevant to the calculations. If we take an algebraic approach, we can solve the problems using simultaneous equations. You have to identify the binding constraints. We don't use the non-binding constraint in our solution. So we've got our two binding constraints, constraint 2 and constraint 3, and then what we do is we take equation 2 and deduct equation 3 from it. And that will leave us 2x1 equaling 7. Because if we take away equation 1 from equation 2, these x2's will cancel each other out. So we get 2x1 equals 7. Therefore, x1 equals 3.5. Now, obviously, we can't have 3.5. So when you're doing it in reality, we'll actually take it down to whole numbers. We will round down because you can't round up, because if I rounded up, I would be outside the feasible region. I would be outside the constraints. I've got to take my 3.5 in my second equation. So my 3.5 into equation 1, or I could put it into equation 2, it doesn't really matter. That will give me my answer of x2 equals 1.5, and we would round that down to 1 in whole numbers. So if the problem relates to units, we cannot have a fraction of the unit. So we tend to round down, because if we rounded up, it would be outside the range of our constraints. So we've looked at a linear programming problem. We've solved it using a graphical technique and using simultaneous equations. Thank you.